everyone. We are 15 here today. It's my great pleasure to introduce you to Maddie, who is the section head for the signal processing CHUV-UNIL, and she will be introducing the speaker.
Hello everyone, I'm super glad to be here in front introducing someone again after a few times. And it's my pleasure to talk about Priscille, just to tell you that she has a background in engineering from CIBM Lyon. And while doing the studies, she already had experience in the University of Michigan. And then as well, she was doing her master project with the Siemens Healthineers here in Lausanne. And we were very lucky that she decided to join us on 2019 already for her PhD funded by the Swiss National Science Foundation that she will explain a little bit more today. So you are already in the third year of the thesis, right? Thanks, Priscille.
Thank you, Mary. Yeah, well, thank you, Mary, for the introduction, and thank you for being here today. So I will present you a work specifically on the segmentation of fetal brain MRI, and specifically how we integrate the topological constraint in the segmentation of the cortical plate. So to give you a little bit of context, as you may know, the development of the human brain is actually a mixture of many complex processes that start even before birth in utero. And in this prenatal period, we observe most significant morphological changes, but not only, as we also see the maturation of the tissues. So it's not quite obvious on this image, but in MR images, we have strong changes in the contrast of the white matter specifically. In clinic, we acquire MR images of low resolution with 6 slices in order to minimize the effect of the fetal motion. And in practice, we actually acquire images from 3 orthogonal planes in order to have as much information as possible. Hopefully, we have super resolution reconstruction algorithms from which, from a set of low resolution images, we can reconstruct one single isotropic, high resolution, and motion-free volume, thanks to which we can then perform additional analysis such as biometric, morphometric, or even volumetric analysis. However, the key asset for the key baseline for such analysis is to have segmentation, as we can see here on the right. But we all know that it's quite difficult to have manual annotations, as it's a time-consuming and very tedious task. So in the recent years, there has been an increasing interest in the development of automatic deep learning-based methods. However, we know that those methods are quite data hungry, and in fetal MRI, we do not have a lot of publicly available data sets. And even when we have some, they are not fully representative of all the variability we can have in fetal brain MRI. The sources of variability, so we have what we already mentioned, the fact that the brain is changing quite a lot, both in terms of growth morphology and maturation throughout the gestation. We have variability that comes from the acquisition with the MR scanner, the acquisition parameters, and so on. And finally, we also have variability that comes from the post-processing methods, which are intensity based on the images and brings in variation between different reconstruction methods. So in this presentation, we will restrict our work to the first variability, as we have images that are all from the same data set and with reconstruction methods. So specifically for the fetal cortical plates, there has been many works recently that focus on the automatic segmentation. Some of them, as we can see on the left, were more focused on the development of optimized protocol to annotate data sets that without any ground truth at the beginning. And on the right, we have an example of a work where they were developing a new module to integrate to another deep learning architecture in order to bring attention within the learning process. However, while all these methods present promising results where the overlap and the distance to the ground truth is always improved. Unfortunately, they never assess the accuracy of the topology of the segmentation. And even worse, in the qualitative results they show in their publication, actually, we see that we have quite big topological inconsistencies. So it's in this context that we want to study how we can integrate the topological constraints in the learning of and the training of segmentation methods, specifically for the segmentation of the cortical plates. We define our segmentation framework, which is just 2D unit architecture, which is widely used for segmentation in medical imaging. And we use a multi-view approach, patch-based, which means that we are working with 2D images, but we fit the network with images from the three orientation, axial, coronal, and sagittal. We define two configurations as a reference to compare our method to. The first one is the baseline, where we train our network with the classical binary cross-entropy loss, which is quite widely used for image segmentation. And the second reference is trained with a hybrid loss, which was proved to be quite to perform quite well in the last FITA MIAL 2021 challenge, where it's just a combination of a binary cross-entropy and a dice loss. And finally, we introduce our method, which is a weighted combination of the binary cross-entropy loss and a new term, which is the topological loss I will briefly introduce in a moment. Before looking at this topological loss, let's talk a little bit about topology, which is actually, topology actually defines the properties of an object that are preserved through deformation. So for instance, when we look at a binary image like this, we can define the Belly numbers, where the Belly number 0 is actually the number of connected components in the image. So here we have only one. And the Belly number of the first dimension is the number of holes in the image. So here, if we do not count the background all around, we have 3 holes. In case where we do not have binary images, we use persistent homology, which consists in tracking the topological structures through filtration of the image. So here we have an example of a persistence barcode for the patch displayed at the top, where we filter the image from 0 with a different threshold from 0 to 1. And at each threshold, we report the different structures we observe. In this barcode, we have one structure, one topological structure. It corresponds to 1 bar, and these bars can be characterized with the birth and the death of the structure, which we can actually see as coordinates in which that we can then display in a persistence diagram, as we can see here. So it's really on the principle of persistent homology that the topological loss is built. And this loss was actually first proposed for the segmentation of neural membrane 2 years ago. And we worked on the generalization of this loss. So in practice, what we want to do is to compare directly our probability map we see here at the top to the ground truth image we aim to generate. What we do is that we first filter both the connected components and the holes in the images with persistent homology, and we report all these different components in the persistence diagram per dimension, so the holes together and the connected components on the other side. And for the computation of the loss, what we do is that we perform a matching between the structures we observe in the predicted probability map, and we compare it to the ground truth. And when we match these pairs, we can actually compute a distance, which is what will result in being our loss that we want to minimize. And finally, as we have different losses for the different structures, we just combine them in a sum to have a global topological loss. We can also generalize this in this formulation with a weighted sum for even more dimension, where, for instance, if we were working with 3D images, we could imagine that we would not imagine it would be that the additional dimension would be to consider the cavities, which are the completely closed holes in the objects. To assess our segmentation in terms of topology, we introduced two new metrics. The first one is the one-dimensional Bally error, which actually consists in quantifying the absolute difference between the theoretical number of holes we should have in our segmentation and the actual number we have in our prediction. While this is a metric that is quite intuitive when we want to compare the topology, we also define the hole ratio, which also brings in information about the size of the hole and the size of the structure we want to segment. The idea here is that we represent it here with the two segmentation B and C, where, for instance, for the B segmentation, we see that we have one big hole, which in terms, if we will look at the Bally number, would be closer to the ground truth. However, when we look at the C segmentation, we have more holes, but of reduced size, which would be more interesting in the work of segmentation. So when we have an accurate ground truth, we would rather use this hole ratio. In our experiment, we use two data sets. The first one is the fetal data set, which is publicly available, in which we work on 37 subjects that we split between the training and the testing sets. And actually, in this data set, they provide manual annotations that were performed following optimized guidelines and then interpolated. And for this reason, the manual annotations are not topologically accurate, as we can see on the left columns for both subjects. And for this reason, we decided to manually correct ourselves the 9 subjects of the testing set in order to have an accurate assessment later on. Another dataset that we use is the spatiotemporal atlas that was published some years ago, where it's quite interesting to have this distribution of one subject per gestational age, such that we can see how we perform throughout gestation. And finally, for the assessments, the global assessment of the different methods, we use 3D metrics, and we use 3 types of metrics that are complementary. The first one is the DICE for to assess the overlap, which is a similarity metric that we want to maximize. And we have 2 different metrics, the average surface distance and the hole ratio, as I presented before, that we want to minimize. We first compare our methods, the 3 methods, the baseline, the hybrid, and our TopoCP methods. And we see that we actually perform a Wilcoxon paired test, where we see that our TopoCP method is significantly performing better regarding all aspects, so the overlap, the distance, and the topology, compared to both the reference methods, the baseline and the hybrid. In terms of qualitative results, we have the white arrows here that evidence areas where we are actually fixing some connections in the cortex that were missed with the baseline and sometimes with the hybrid methods. And additionally, we see for the old subjects, in the white circles, maybe you cannot really see it actually, but those are areas where the cortex is better segmented in depth of the gerification. As I was saying before, we can also perform a gestational age based analysis. So this is with the atlas, where the first observation is that between about 23 to 30 weeks of gestation, we have much better segmentation performances, and also all the methods are quite equivalent. We have two hypotheses for this. The first one is that this is the gestational age range that is the most represented in the training set. And the other factor is that for old fetuses, so that we would consider above 30 weeks old, the morphology is much more complex as all the gerification pattern started. And for this reason, it's a bit more tricky to segment. However, except for the outlier we see here at 38 weeks old for the distance metric, we see that it is for the old fetuses, so above 30 weeks old, that our TopoCP method benefits the more for the segmentation. We also compare our automatic methods to the manual semi-automatic method segmentation that were provided in the data set originally. So again, we perform a Wilcoxon paired test where we see that we are performing better in all aspects of the segmentation compared to the manual annotation. And we evidence here in the 3D rendering the false negative that are actually connected to the holes in the true cortex. And we see that we have way more holes, it's way more noisy, the segmentation of the manual annotations. So they were actually performed the one slice every second or slice. They are annotated one the brain every second or third slice, and then they interpolated, which resulted in a very noisy annotations. To conclude, so we saw that we are actually improving quite a lot the topology, but not only the topology with the shape correctness, but also the similarity with the overlap and the distance to the ground truth. And the metrics we observed were all performed in 3D, especially for the topology, while we were using 2D/2.5D as we were still having 3D informations. Another good aspect of it is that this loss is actually architecture agnostic. So this means that here we were using a UNet, but we could actually use it with any network that is providing a per pixel probability. And the future work would be more oriented on the generalization, which would be, first of all, to address the different, the two other variability I mentioned at the beginning, which are linked to the acquisition parameters and the post-processing methods. So that could be to use other data sets or other images from different centers. And another generalization would be to work on other structures which would have different topological features, or to work on multi-tissue segmentation. And with this, I will thank the MIAL team, which is quite photogenic here, and I will thank you all for your attention.